Hello, my name is Professor Victor Chang, or you can pronounce it Chang. So I'm very honored to give a talk of my another paper on SCIQ1. The title is called Pima Indian Diabetes Mellitus Classification based on machine learning algorithms. And as we know, diabetes has been around for a long time. It's a disease for many people. So in this paper, we propose a diagnosis system based on machine learning ML algorithms to be implemented on the Internet of Medical Things, or IoMT, because it's very important for us to demonstrate the interdisciplinary research, and we have to offer something extremely new. So in this case, that we offer the diagnosis for the diabetes mellitus or type 2 diabetes. And as we know, the machine learning algorithm tend to be mistrusted because of various reasons. So one of them is the inability to show the internal decision-making process, resulting in slow uptake by end users within certain healthcare sector. So in this research, that as we know, there are many machine learning models. So we have chosen 3 of them, which are known as the naive Bayes, random forest classifier, and the J48 decision tree models. So to be trained and tested using the Pima Indian diabetes, there's in this case we are also using other languages. So the performance of each algorithm is analyzed to determine the one with the best accuracy, precision, sensitivity, and specificity. So it can be conducted that the naive Bayes model works well with a more fine-tuned selection of features for binary classification, and the random forest works better with more features. So this is giving you a nutshell for the summary. So for the challenge, what we have is that every detection and diagnosis of pre-existing non-communicable diseases can prove it quite difficult, while patients are, susceptible to infectious diseases. So patients may be prone to different types of infectious diseases. So we need to have something that will help the decision-making to be more smoothly delivered. And also we have a good level of accuracy. And also the lack of the explainability in machine learning models causes there are certain skepticism and also criticism by consumers, and result in slow uptake by end users within the health sector, where mistake could be fatal. So we should not make mistakes, and also we should introduce explainable AI to ensure that everything can be explained, and we need to be 100% very sure that all the results will provide the meanings to the end users and patients, and do not cause any harms. So the objective is that the e-diagnosis system, it will allow us to develop an e-diagnosis system to detect and classify diabetes as the IoMT application, and so that we can then prevent whether a person is at risk for diabetes based on several risk factors, and to provide doctors with some kind of preliminary diagnosis so that they can make a better decision and judgment, and to provide the doctors guidance on diet, exercise, the blood glucose testing to patients. As we know, there's much data about patient, so that we need to provide the most important data for the doctors. So in this case, we should not have too many algorithms, because it's going to confuse to the end user, such as the doctors. So we have selected 3 of them, and that's based on the previous experience and also the pre-processing output. So without going through in details, and I'm going to discuss them a little bit further, why those 3. So just to give you a summary, this is e-diagnosis. So at the beginning, you will then see the hospital and the community connect to the patient, and with a large hospital and a doctor. Medical doctors are the one to connect to various places, and the patient, of course, the one from the patient is to provide the data it will be into the system. So e-diagnosis system is based on the one on the right. So the patients there will get into pre-processing, and there will be best classifier, and to inform the doctors about the preliminary diagnosis. So our contributions are more on this aspect, on the e-diagnosis system, especially when we have new data such as the diabetes databases. So what we do is that we involve with the data pre-processing to understand what are the important things, and to also perform data cleaning, and also to make sure all the data is in a unified format, and then we then perform some advanced analysis, such as feature selection based on very important variables or the key variables. Then we then use a pre-identified machine learning algorithms, such as the J48 decision tree, random forest, and naive Bayes. So our contribution is focused on this part, and our result will then provide meaningful outputs for the best classifier for the doctors. So in this case, as the Internet of Medical Things, as we know that so many technology need to be merging together to solve the problem together. So the IoMT enables the medical systems, application, and devices to connect to each other. Then the patients can upload immediately measurable medical indicator remotely to the e-diagnosis system. So to provide doctors with a preliminary diagnosis, because the diagnosis may take time and it's not convenient, especially when patients may have the disabilities or may have certain illnesses that prevent him or her to go to the hospital easily. And also, there are certain cases that you need to know result, which cannot take for weeks. You need to know the result within days. And in that case, the patient's profile can be accessed by doctors remotely through the internet and shared by the doctors from different medical institutions. Of course, there must be a very strong GDPR and security in this place. However, our focus in this case is more on the diagnosis aspect and how our algorithm will help with the diagnosis. And then, of course, we will be very interested to talk about security, but not in this paper. And the advantages of combining the e-diagnosis system to the Internet of Medical Things. So first, the amount of paper-based medical records can be reduced to a large extent, and the patient does not need to go to the same hospital, even to the hospital for follow-up visit in person, because normally most of the time will be spent on the trouble and also to get to the waiting room in a hospital, and more time should be spent on getting the result analysis, and also to speed up the process with the IoMT, remote monitoring and management of chronic illness, as well as the accessibility to qualify the healthcare for patients will be helpful. And also we can ease the data collection and analysis, as well as the improved healthcare data, which can improve the e-diagnosis system and algorithms. So we then talk about the data and methodology. First of all, I'm just briefly talk about the algorithm. So in this case, J48 stands for a specific algorithm for decision tree. As you can know, it's a kind of supervised machine learning algorithm. And you can see in this simple example, yes or no. Then you can then get the probability for this, and then you will give you a result in a short period of time. And then a leaf node is a decision tree represent the classification outcomes, and the internal node represent the judgment of attribute. The first step to select the most appropriate attributes for the root node. Then the instances are divided into number of subsets you can see here. And then for each subset, the instances are supposed to have the identical attribute values. So each subset will be repeated recursively until all instances have identical classes. So random forest is an extension of decision tree, and composed of numerous single decision trees. So each of them produces a category or prediction result. So there are 9 decision trees in a random forest, then the prediction result of 6 1, and the rest of the 3 will be 0. So the prediction result of RF is 1. So it means that there are more predicting 1, then of course, then the one with the majority win. So the key, if for the good performance for this classifier, is the trees in the forest are relatively unrelated to each other to ensure the decision they make as a whole is better than the decision made by each of them individually. And naive Bayes, the Bayesian classifier is a statistical classifier and is operated based on Bayes' theorem, classifying data into the predetermined categories using the condition probability. As you can see, in this condition, you will get into 3 classifiers identified by different colors. So naive Bayes is regarded as the descriptive as well as the predictive algorithm. The probabilities are descriptive and then employed to predict the categories of the untrained data. The advantages will include, first, it's easy to use. Second, the amount of training data needs for classification is not necessarily large. Then third, although the classifier is naively design. And assumptions seem to be too simple, but of course you can perform it well a number of ways. So as long as you fulfill the condition in a way that you can get the results. And then just to make everything short and precise, now I'm talking about the data set. So you can download data set. So every research we do, we need to have something that you can check. Of course, you can then find out other type of papers by similar approaches or by other researchers. But in this case, let's look at the data set. So these are the important features. Of course, there are also other features. So there are a number of times that the woman get pregnant, and then you get a range of 0 to 17, and the glucose, the plasma glucose concentration at 2 hours, and then BP stand for diagnostic blood pressure, and the Trapset scheme for thickness, because when you have the type 2 diabetes, sometimes you have to inject insulin, and therefore the skin thickness is also a factor. And of course, the insulin, the 2-hour insulin serum, and the BMI, the body mass index, DPF, the diabetes pedigree function, age, and the outcome. So we have the binary classification task with 0 indicate negative test for diabetes, and 1 implies a positive test. So there are 8 features and 768 sampled. So there are 500 non-diabetes patient and 268 diabetes patient. So the experiment designed in this way, there are 3 algorithms being used that which I've explained. So there are at least 3 experiments. So first of all, we include all the features: the glucose, BMI, age, insulin, skin thickness, and DPF, blood pressure, and pregnancies. The second experiment, the 3 features: the glucose, BMI, and age. And the experiment 3, there will be 5 features, which means glucose, BMI, age, insulin, and skin thickness. So for the feature selection, as you can see, the rule here, it then gives the error that will be close to each other. And then you can see when we then run everything together. So first of all, when you are doing the data analysis, the first approach is to then go through with everything and see how different results or data say they are related to each other. So in this case, this gives two different directions, and there will be 3 different directions following for this. So as you perform more and more, you will see that the pregnancy and age, they have the close correlation. Then the glucose and blood pressure, they do have correlation, and BMI, DPF, insulin level, and skin thickness, they have another. So then we perform another way for feature selection. Then we use the K equal to 2, 3, 4. Of course, you can also go for more for K-means clustering. And then K equal to 2 has the best separation or boundary of the groupings. As you can see, they are very clear-cut. But then when the K clustering means the variable goes up, then you see that they begin to converge and there are something in common. Then feature selection, if we go for the 5 features that rank according to the outcomes, then we got the glucose, BMI, age, and importance score over 56. Insulin, skin, and importance score over 20, which the higher the score means that they are more closely related to this, or there are some indication for correlation, and then further analysis will be helpful. Then the AUC ROC curve, as we know, the receiver operating characteristics, which stand for ROC curve, and the resulting area under the curve, AUC, that provide a very crucial performance measurement for classification models and to represent the degree of the separability of classes. So AUC measure the entire 2-dimensional area underneath the entire ROC curve, from 0.0 to 1 to 1.1, with a maximum value of 1. So ROC curves for all the models using the 3-factor subset and 5-factor subset and a full data set. So we then show the result here. As you see that all of them will get converged to 1 for sensitivity. But then the values for the most appropriate ones or most valuable ones are being recorded here. So then we run with the 3 machine learning algorithms, we get the best AUC output. So it will indicate that most of them are doing quite well to perform under normal circumstances. We do not do overfitting. We do not try to, in order to get the result to sharpen up the for the analysis. So then we perform the analysis. We get fairly good outcomes of 80% plus for all the three machine learning algorithms. And similarly, we have 5-factor ROC curve. They also behave the same. However, there's slightly drop of performance compared to 3-factor ROC curve. But also, we will discuss a little bit more. We then use accuracy, precision, sensitivity, specificity, F score, and AUC. And then we explain the formulas on the paper. Due to the shortage of time, we also have performed some numerical analysis. And then we explain the reasons for doing those analyses. But in this case, we just want to present the most important results. So I hope all of you will follow, and the random forest classifier in this case outperformed the naive Bayes and J48 decision tree with an accuracy metrics of the nearly 80% and precision very close to 90%, specificity as 75%, F score 85%, and AUC 86%. As you can see, then we perform those key matrices with these three machine learning algorithms, and then J48 decision tree has the best sensitivity outputs. And then for the random forest, with the precision with the highest and also very high results for F score and AUC. And for naive Bayes, we also have very good results for sensitivity and also F score and AUC. However, the specificity doesn't score well. And then we can make a comparison between the three machine learning algorithms. And similarly, we do this for 3-factor and 5-factor data sets and the analysis. As you can see, the 3-factor, the J48 decision tree has the highest, very close to 90%. And then with random forest, we will get a very equally distributed outcomes. And then we get about 82.12%. And for the precision, and then for the naive Bayes, we have very high results for the last two, the F score and AUC. And the one is very close to 85%, one is slightly above 86%. So the naive Bayes model on the 3-factor data subset perform just as well as the random forest model on the full data set. We then can conclude the naive Bayes model works well with a more fine-tuned selection of features for binary classification, but falls short with numerous correlated features, while random forest works better with more features. So if you want to go for more features, you go for random forest. But if you want to get individual performance, then the other two seem to work well. So they're different machine learning algorithms serving for different purposes. And the J48 decision tree model consistently perform with the sensitivity rate range of 88% plus for the full data set, or the 89.92, very close to 90% on 5-factor data subset. So it shows it's quite good at predicting the presence of diabetics, no matter how many features it has to work with. So it's pretty consistent with J48 decision tree. And the conclusion is the summary of this study. We can use the 3 machine learning algorithms to present a classification model suitable for electronic diagnosis system to be implemented for the Internet of Medical Things, IOMT. As we know, we should merge different technology together to solve a more challenging problem. And the top 5 most important features indicated by selection methodologies are in line with the existing guideline. The models are close to 80% accuracy in general, but without overfitting. We are not trying to sharpen up result and so, but then in other matrices, we can get as close as to 90%. However, that may also mean we may either consider other develop machine learning algorithm or integrate different machine learning algorithm together, or maybe to understand the data set with more sophisticated methods. So we will enhance the data, of course, because the quality of data matters a lot for data science, and data pre-processing techniques and algorithm for better analysis, because the certain records on the data set may be not getting as good as quality as we hope for, or maybe there could be some patients or non-patients, even at a selection stage, there is something that we cannot control, or maybe there can be patients on the recovery, no longer having diabetes, or maybe they suffer the diabetes again. The kind of thing we cannot control. So at least that we maintain a good percentage of accuracy, and other matrices close to 90%. So the new automation and automated process for IOMT will be developed, because it's so important. Currently, a lot of work is done on the manual way of doing things, and there are high expectations on the data scientists. So in the next few years, hopefully all this will be automated. And why should you cite our paper? That's the most important thing for this presentation. First of all, we can predict whether a person is at risk of diabetes based on several risk factors. So you can provide 3 risk factor or 5 risk factors. So it's giving you a very simple and convenient way to use the power that e-diagnosis system to provide a preliminary diagnosis to support the doctor's own diagnosis. We then can help the medical doctors in their work, and to feedback the doctor's guidance on diet, exercise, blood glucose testing to the patient, because there's much data on the patient, and now it will help the doctors to make a better judgment and better advice. So to make the model clear and understandable to end users, that's also crucial in the research now, because we have to apply what we do to everyday real-world solution. So we provide several useful analyses and the interpretations, and we present how we judge which features are important. We then make the most important the decision for the doctor, so they can focus on the important features and the variable. We discuss how the choice of the features affect the model's prediction results. So if you can, please visit this paper. The link is here, and then we are going to put the link on the YouTube channel. Thank you so much for your time. We really appreciate, and we wish you all the best. Thank you. Have a good day, and we'll see you later. Bye.